So a while back I made a video where I showcased how to do some basic plotting of the Mandelbrot set using Python. But I kind of skipped the most important part of, or the most fun part of fractals, which is to do the infinite zoom. So now I'm going to do another video to show you how to do something like that. So just a quick recap. The Mandelbrot set, for a point to lie in the Mandelbrot set, means that you feed the output of a function, call it f, takes two arguments, set and z, which returns z squared plus c. And the point c in the complex plane belongs to the Mandelbrot set if this function, when you feed the output back into itself, a number of times, if it diverges, that means that the point does not belong in the Mandelbrot set. So we need to make a function. We can call it diverge, which takes the point c, and also a number of iterations, call it max iter. It's set the default to 20. So we should write a, well, first we should just initialize z to be 0. And also we should force this number c to be a complex number. So in the case where we want to input a tuple or a list of length 2, we can just unpack it and put it inside of this complex keyword here. So now we can write our loop. So for I in range max iter, we want to update z to be equal to, what's that, z squared plus c. And also we should do a check. So we need to set some kind of boundary if it's going to escape, diverge or not. And a common boundary for this, or condition, is the following. If the coefficients, so z at this point is also a complex number, z dot real, the real part of it, coefficient, plus z dot imag, the imaginary part of it, if they exceed 4, then it will diverge. So then we will just return I, the number of iterations. And if not, then we are just going to return 0, saying that it does belong to the set. So we can try to test that out. Diverge, we'll see, could be a point, say 0, 0. That should be in the set, and it shows 0. So that's what we would expect. So now we need a function to make the grid for which, like in the complex plane that we're going to plot. So we're going to call this make grid, and it needs to take some parameters. I'm just going to call them b box, bounding box, and the bounding box will define the minimum and maximum of the coordinates. So I'm going to call them x min, x max, y min, and y max. I'm just going to unpack those. And now we're going to use this numpy mesh grid function. So we're going to say x, x, y, y equals to numpy mesh grid. And into that we're going to feed it linspace, which will generate a vector of equally spaced numbers. So from x min to x max, and we want, well, how many steps do we want from A to B? Well, we want that to be our resolution. We're going to call that res. We have to put this in as a parameter, resolution. So we've done that for the x, and we can also do that for our y. Let's see here, think like this, the y min and y max. And now I have to pair these coordinates together. as to make a list of coordinates. And then the way we do that is that we use the numpy.c concatenation. So here we pass in xx.revel and yy.revel. And I think that should be sufficient. So we can again test it out, make grid, and we're going to pass in a bounding box. CB box equals the points, I think these are good points, minus 2.1, 1, minus 1.3, 1.3. That will make a nice symmetrical image. So make grid bounding box. We can set the resolution default to 150. Let's see. Oh, of course I have to return the coordinates. Return coords. And yeah, there you go. So here are our coordinates. Now that's been done, we need to make a final function that will compute whether or not each point lies in the Mandelbrot set. So we're going to apply this diverge function to makeGrid, the output of makeGrid. We're going to call this function make Mandelbrot. So it has to intake the coordinates, and that I think maybe some more arguments, we'll see. So we call it MB. Can do a list comprehension where we apply diverge C for C in coordinates. And now we'll get a long vector, basically of yes, no, belongs or does not belong in the Mandelbrot set. Or rather, actually, also the number of iterations for escape time. But we need to reshape it to fit like into a grid, so we can plot it finally. So actually we have to make this into a numpy array so we can reshape it. So we need to do mb.reshape, and the shape should be the resolution times the resolution, right? So we're gonna, let's see, I have to pass in here, I think maybe it's a tuple res. So we need to define the resolution. We could input this into here, but since we already input that number into this function, I don't like to repeat the same arguments to feed them in multiple functions, so I'm just going to recompute it. So the resolution is going to be, that is going to be the square of the shape of the coordinates. So numpy dot, or the square root, sorry, numpy dot square root of chords dot shape 0, and then we can force this to be an integer using the as type int. Just see that. Let's see, what do you call that? Define. So far so good. And then of course we have to return this, return MB. But also we should have an optional plotting option here. So let's say plotting, set the default to true, or plot equals true. If plot, then we're going to make this figure. So plt.imshow MB, and we can set the color map to be, I think GNU plot2 is alright. And then do a plt.show. Let's see if this works. So let's just set our bounding box. We already have our bounding box. It's defined above. Just copy this cell down here. And we can say chords equals make grid. And then we can do make Mandelbrot chords. See, it throws an error. shape for image data. So maybe did I input this incorrectly? Square root chord shape 1. Let's see. Chords shape. What's the square root of that? Numpy square root 500 150. Shouldn't that be fine? Maybe I have to set it like this. That's strange. Alright, looks like that works. So here is our basic image. The resolution is kind of low, you can always change that later, but now we just care that we don't have to wait for too long. So okay, that's the basic plotting function. So now we need to make a zoom function, and that's kind of the point. We need to define some focal point from which into which we want to zoom. So let's make this function. So let's call this function zoom, and again we have to take this bounding box. We need a point, we can call it P or maybe FP for focal point, and then a factor of how many times do you want to zoom in to that point. So let's see. We need to say, we can say x, y equals fp, so unpack that point. And so we're basically going to shrink the x. We want to keep the proportions the same as in the bounding box. We only want to shrink it by a matter of this factor right here, centered around this. So again, we can say unpack the b box, x min, x max. Oh, be consistent here on my naming. Y min, y max equals bounding box. So x range, well, that is the width, the new width is going to be x max minus x min, but we want to decrease it by a factor of factor, right? So a factor equals to 2, that is going to half this distance, the width. And same with the height, or the y range. It's y max minus y min. Divide this by the factor. And now we're going to return a new bounding box, essentially. So the new bounding box is going to be x, this point, plus, well, first x minus the width, and then x plus the width, and the same with the height. And actually, because I think actually we should, let me see here. Yeah, I think the factor should actually be multiplied by 2 here, but it's not very important. You can just do it like this. So x minus the width, x plus width, y minus the height, and y plus the height. So let's see, return this tuple right here. And I think that's all that we need. We can test it. Zoom, b-box, focal point can be 0. Let's call it p equals 0, 0. And b-box p, let's see. Yeah, so that doesn't seem to make much sense because the factor is 2, so I did have to actually multiply it by 2 because I'm adding it on both ends. So multiply by factor, I can just say factor equals factor times 2. And yeah, that looks about right, halving the distance around the center, so that's good. So all our functions now seem to work, so now we can basically tie it together, but we need to find some point that we're interested in. And you could try to identify that yourself. You could also just find some interesting points by Googling that question. Interesting points. So I'm going to go and do that. So I went ahead and found someone claiming on Quora that this is an interesting point. So we can try to look into this and have a look. So that's our P. Now we should basically just make a loop where we zoom in a number of times and plot the result. So let's just make this loop for I in range. I don't know how deep we need to go. We can just start by doing 10. So also we should just have our bounding box for starters. Okay. So at each point we're going to say update the bounding box, equal that to zoom bounding box, and P. The factor can, well, so far can just be 2. And then we want to compute the coordinates from this bounding box. So we have this make grid function, make grid bounding box, and finally we can run this make Mandelbrot function, make Mandelbrot chords. So let's see if this works. Well, it does plot, but it wasn't very interesting. Maybe we have to increase that number of iterations to diverge. So what we can do then, we'll just keep this here. We can import from func_tools, import partial. So I'm gonna make a new diverge function. Actually, we could pass it in here. I think I'm just gonna update this value here. So diverge, or that is, it would be nice to be a little bit more flexible. So actually I'm gonna do that. I'm gonna input another argument, a function, div. We're gonna call this div instead. So that will give me a little bit more flexibility because I can pass in div, and I'm gonna say div equals partial diverge, and then we're gonna pass in this keyword argument, max iter, and say what happens if we increase this, if it's gonna increase the resolution. Now still it didn't give very interesting results. Okay, I'm gonna look a little bit into this and see if I can find the solution. So after a while of troubleshooting, I found that I could pick some other points and I didn't have that same problem. So just to show another point here, you can zoom in and you don't get those kind of ugly figures. But now we run into another problem of an overflow from complex exponentiation, which I also found out was simple to solve. I don't know why it works, but if I simply go back up to this function, diverge function, and when I test for this condition, I basically just square these exponents and I rerun, and I shouldn't get the problem of overflow error. Well, you see it is slightly slow It was a bit slower now, but at least we can keep zooming in. So that's quite all right. And we can also maybe we can try the first point again. See if this will yield a better result. No, still the same. Now there is one issue when you're doing this plotting, that you will see that kind of the granularity or the detail gets lost the more you zoom in. And the reason for this, I found, is that kind of the closer you are to this edge between the Mandelbrot set and the points outside the set, the larger the number of iterations you have to do. So what you should do is that you should dynamically update this function. Let's call it div here, and call it, let's see, diverge max iter equals to, we can start at the level of 20, but we have to increase it. And I don't know the best way to do this. Maybe you're just gonna have to experiment or Google the best way to do it, but I'm just gonna do a kind of linear increase. So the number of iterations multiplied by, maybe increase it by 5 for each iteration. So we can start by having it at 20, and then we keep increasing. Let's see if that's going to make it better. Yeah, and here it looks like you have some more detail than you did previously. If we increase this number, like increase it by 10 every time, maybe we can go deeper. And of course, it's always going to be slower every time you do this, and that's kind of the drawback. Yeah, you see it's much more detailed now. Much more detailed. Still keeping the resolution quite low here. And of course, you can change this yourself. Now it's just a matter of the demonstration. Okay, it seems like we have to kind of increase it faster. Or maybe you need to do some kind of super linear increase. But again, you can look into that yourself at some point. But at least now we have the basic kind of function for doing that. And now we of course can make an animation from it. So whoops, let's interrupt that. So we should add another functionality in our function here in the make Mandelbrot. So we should have the option to save the figure. And I'm just going to say input file name and set the default to false. And then I'm going to say if file name, so if you pass in a string for the file name. That's the nice thing about dynamic typing in Python. If file name, then we're going to call plt.savefig. And then I've already made a folder called figures. And then we're going to have, so we can use this, make an f string. So we can input here the file name dot png. And that should save that into the figures directory. Actually, I think I might want to do this before we call plt.show, or else we might have some issues. Okay. Yeah, I think I don't think we need to do anything more than that at this point. So let's just try to test this. Then we need to define a file name, and that can be the zoom factor. So let's define this above as a parameter. Zoom factor equals to 2. Factor equals zoom factor. And then the file name can be, again, we can use an f string. Mandelbrot zoom underscore, and then I multiplied by that zoom factor. I times zoom factor. And then we can pass in this file name equals file name. Now we can see if that works. Yeah, that worked for me. So now what I can do is that I can basically make an animation using these pictures, make a GIF, and with that I can use the first I want to import OS and also imageio. First I want to do an OS file names equals os.scander figures. I'm just going to look at those files, see if we can find them, and yes, that's fine. Now these are dir entries, so we can do fn.name for fn in file names instead, and that's going to give us just the string of the name. And here you see kind of an annoying thing in Python or in any with computers. When you sort them alphabetically in alphabetical order, they're not going to be sorted in numerical order. So you see 0 comes, then 10, then 12, and like later comes 2. So we need to fix this naming problem, and we can do some kind of zero padding for that. So let me just write a function for that. Def 0 pad, input a number and a number of zeros. Let's call that L. So we want to take an integer, that's the number, and we want to compute the length of that, like in terms of how many figures, like this has 2 figures. So then we convert it into a string, and we can call len on that. What would you call that? Maybe we could call this variable here the parameter number of zeros. And we call this L. And now we have to return, well, we want, when we have more of these figures, we have fewer zeros. So we'll have number of zeros minus this number L. And this should be the number of zeros that we trail before it. Just multiply that. The string, when you multiply strings, you just concatenate. So you should return this and then concatenate this number again. Let's see if this works. So just for I in range 20, print 0 pad I. Let's set the number of zeros to 3 as a default. Yeah, and that seems to work. So now it will be nice and alphabetical when you sort it like that. So we go back up and we say file name equals 0 pad, and then this number here instead. So do that. All right, so this finished running now, and we can, once again, we can try to run this here. And yes, now you see that it's nice and orderly. And now we can string them together and make an animated GIF. I'm just going to find some code for that quickly. Okay, so I found some old code for that. So basically you just make a empty list, and you loop through these file names, and you just append the file using this imageio imread. And once you've made that list, you can just use imageio.mim save, and then you make give it a name, and that should work. Okay, so once you run this, you can look at that file. You can actually embed this in Jupyter if this is a markdown cell using some HTML code. So like this, I call it zoom.gif, and there you have it. So of course this is a very slow algorithm. It's not optimized at all, so I don't recommend doing like these super deep zooms using this. It will be very slow. Of course you probably can do it, but I would look more into how to make the code run faster before doing that. Yeah, I think that basically shows you the basics of how to make the Mandelbrot zoom. Thank you for watching.